Hello, welcome to the first session of Flipped Classroom Environment for Statistics here at AUK. This is Muhaxheri. In this chapter we'll be looking at descriptive statistics. Descriptive statistics can be thought of as having two parts, the visual part and the numerical part. In this chapter we will be going over the numerical part. Okay, let's move on to the next slide. Okay. First and foremost, some key terms. Okay, data arrays are simply orderly representation of data, either in an increasing or decreasing order. Think, for example, of a group of students in your section. If I were to ask you your ages, you would all be seated randomly, and therefore I would note down the ages as you give them out to me. They don't necessarily are from highest to lowest or lowest to highest. Once I arrange them from either lowest to highest or highest to lowest, that's called a data array. And data arrays are very important because they allow us to more simply analyze data, and sometimes they're necessary in order to move on onto another section. The next thing is stem and leaf display. This is a combination of graphing and sorting techniques of the actual raw data that are taken out. It is very useful when dealing with small numbers of data. We're going to see an example in a minute and you understand better what it is. Frequency distributions. Quite often in a newspaper or some book or some article, you see a newspaper, you see a table rather, which has some categories, and then it has numbers next to them which represent how many belong in each category. Essentially, that is a frequency distribution. There is some sort of a technique in order to create one of those, and later on in this chapter you will see how we do that. And if you were to take that frequency distribution and create a bar chart out of it, that's effectively called a histogram. Now, the last thing in these key terms we're going to talk about is something called box plots. We're going to talk more about box plots in our next session and through examples in class, but essentially a box plot is a graphical representation where you can tell immediately where 50% of the middle of the data lie in. Okay. Now let's move on to the stem and leaf. As I said earlier, data arrays are highly important, and the first thing when dealing with stem and leaf displays is what you do is you arrange the raw data into a data array, either from highest to lowest or lowest to highest. The stem is the leading digit or the leading digits of the data, while the leaf is the trailing digit. The important thing about stem and leaf, okay, that all the data, all the raw data are still there. No information is lost, so you can always go back to the previous data. Now, imagine the following example. Okay, let's say we have 30 test scores for a statistics section. Okay, the first student got a 71, the second student an 85, the third student a 62, and all the way down to the bottom right to the last student who got an 82. What happens here is, if you think of this number, 71, okay, the leaf is the 1 and the stem is the 7. In this second number, the leaf is the 5 and the stem is the 8. So all these numbers, the last digit, the trailing digits, are the leaves, and the leading digits, like this, like this, like this, are the stems. So now what happens when we create a stem and leaf display? Essentially, we create a chart such as this. Okay, all the stems, so the 5, the 6, the 7, the 8, and the 9, these represent the 50, the 60, the 70, the 80, and the 90 odd percents, and the leaves are all the other digits to the right. So one student got a 52%, another student got a 53%, a third student got a 54, and so on. Note immediately that we know that two students got 63s, two students got 68s, for example, two students got 80%, the lowest student got a 52, the highest student got a 92, and the most majority, if you were to categorize them, were somewhere in this area, in their 70s. So that's essentially what a stem and leaf display is a graphical representation of data. It sorts out the data at the same time, and it's all the information is still there. Nothing is lost. You can still go back from that slide and recreate these original data that we had in the previous slide. Now, the frequency distribution. The interesting thing about frequency distributions is that it has a number of things that make it up. Okay? Those things that I talked about, I said you look at the newspaper, for example, or some article or a textbook, and you see a table and you have these categories. These categories are called classes. In each, for example, in our classroom, we may have a group of students that are in the age range between 18 and 20, some students in the age range between just 20 and 22, 22 to 24, and so on. And then we count how many belong in each age range. Those values which tell us how many belong in each one are called frequencies. Those age ranges, for example 18 to 20, are called class limits, and they represent these boundaries for each class. Okay? Whereas the width of each class, say 18 to 20 has a width of 2, 20 to 22 has a width of 2, and so on. They're called class intervals. There is also one other important point. It's called the class mark, and the class mark is the midpoint of each class. For example, in the age range 18 to 20, the class mark or the midpoint would be 19. On the age range 20 to 22, a class point would be, or rather a class mark would be the midpoint, which is 21. One important point about class marks is that we use them to estimate values when the original data are missing, to estimate the values of something called the mean, which you all know it as the average, and something else we're going to look at later on in the course called the standard deviation. Now, there is some logic to creating a frequency distribution. Okay? First and foremost, you can't have too many or too few classes. Okay? The important thing is that it has to look easy on the eye. Okay? The information has to have some optimum about it. Too few doesn't tell you much. Too many values in there, it just eats up too much of your brain power. In other words, you should be able to get a rough idea by just looking at the frequency distribution. Now, a way of deciding on how many classes should you have is to look at this rule called the Sturgis rule. The Sturgis rule gives you an approximate number of classes. It starts off by creating a value using this formula. Okay? This k is the approximate number of classes. Okay? And n is the number in the data set. Imagine you have a large data set, a set of 5,000 values. Okay? All you do is put that 5,000 instead of n in there. Okay? And the logarithm of 10 ensures that the number of classes is kept down. It doesn't shoot off exponentially. Okay? Now, in an example we're going to see in a minute, you'll see how easy it is to deal with these. However, how do we actually construct one of these frequency distributions? First and foremost, you go and have an approximate number of classes for the data that you have. The Sturgis rule you just saw helps with that. Okay? Once you get that value, once you get the Sturgis rule, then you find out the range. The range effectively is the largest value minus the smallest value. Okay? Imagine that the difference between the oldest and the youngest person in the room is 10 years. And we need to have 5 classes. Okay? That's how we do the class interval. We do 10 over 5. That gives us an approximate class interval of 2. Okay, so we divide the approximate number of classes, which we found using the Sturgis rule, into the range. Okay, The next step is we round that estimate from step 2, okay, to a convenient value. You can't have groups of 3.5 students, for example, belonging in some group. You can either have a group of 3 or a group of 4. So you have to make sense of these. It has to be easy on the eye, and most importantly, it must follow some common sense. Okay. Then you select the lowest class limit. In other words, the lower class limit for the first class, for the first category. Ideally, once you've arranged the data into a data array, you select the lowest value, okay, and then you choose something smaller than that. That should be the lower class limit for the first class, bearing in mind that sometimes it's not possible or it doesn't make sense. Imagine you're trying to find out the amount of alcohol in the blood, and the lowest value that you can have is 0, no alcohol in your blood. You can't say, well, let's start at a -1, because having a value of -1 does not make sense. You cannot have a negative amount of alcohol in your blood. So once you've selected the lower class limit for the first class, you start adding repeatedly, okay, the values that you determined, i.e. the class intervals, to create the upper class limit, and you keep doing that until you reach the end class. In other words, all the values have been included. Okay? And the last step is to define the classes. Sometimes when you're dealing with large amounts of data, it's easier to view them as percentages, to make more sense by having percentages rather than the actual values. Imagine you're dealing with data in the thousands rather than saying I have 3,500 out of 5,000 in this category. It is much easier to say, oh, there is 70% in this category. Okay, so how do we create this relative frequency which expresses percentages? The classes we've defined in step 6 previously. Okay. What we do is then we look at the frequencies, i.e. how many in each class, and we sum them all up. That's step 2. Finally, we say, well, how many in each class do we have? How many students in each age range? And each of that value you divide by the sum from step 2, and that is effectively a relative frequency. Now, those values can either be expressed as decimals or as percentages. Either way it's okay, but you must, I emphasize the must, you must be consistent. Okay? An example in a minute will show you how easy it is to deal with these things. How actually do you construct something else now? Something called a cumulative frequency distribution or a cumulative relative frequency distribution. Well, let's go back to the idea of having, say, 3 age ranges in your classroom. One being those that have definite values. Imagine that there are 20 students in the group. Okay? Then 5 of them belong in the age range between 18 to under 20. We say under 20 by convention. And then 10 belong in the age group between 20 to under 22. And lastly, 5 belong in the age range between 5 and under 24. Why do we say under? Because, for example, if you have categories 18 to under 20 and 20 to under 22, if someone is age 20, they cannot be in both categories. So they only be in the category which includes 20 as the lower limit and not as the upper limit. Now, a cumulative frequency distribution means that we know that there are 5 students who are between the age of 18 to under 20, but in total 15 students who are in the group range between 18 and under 22, and overall 20 students who are between the ages of 18 and under 24. So we just keep adding the frequencies as we move along, so we keep accumulating. If we're talking about a relative frequency distribution, that is essentially the same thing, however we do add up the percentages found earlier in the relative frequency distribution. Let's look at an example and see how easy it is to deal with these, because sometimes only through examples things can actually fall into place like a puzzle. The average daily cost to community hospitals for patient stays during 1993 for each of the 50 US states is given in the next table, and we're asked to do the following. A. Arrange these data into an array. B. Approximately how many classes would be appropriate for these data. C. Construct a frequency distribution, state interval width and class mark. And D. Construct a histogram, a relative frequency distribution, and a cumulative relative frequency distribution. Now, these are the data. Note that they are arranged alphabetically. So in Alabama, the average daily cost was $775, and then we go through Arkansas and all the way through to Wyoming in the bottom right hand corner at $537. The first step, if you recall, is to arrange these data into an array. So if we move on and arrange them from, say, largest to lowest, we can immediately tell now that California has the largest value. Note that $1,221 of daily cost per patient, versus Montana was the lowest at bottom right hand corner of $482, and all the other states in between somewhere. The next step is for us to create that frequency distribution. And how do we do that? Okay. Well, first we must approximate the number of classes we should use in creating the frequency distribution. The Sturgis rule, which we saw earlier, gives us the starting point. There are 50 states, so we have 50 numbers, therefore n is 50. Substituting 50 instead of n gives us a value of 6.64, which is approximately 7 classes. So Sturgis rule is telling us you should have approximately 7 classes. It's not saying definitely, approximately. So around 7, this should be the optimum value. The next step is that we calculate our range. Recall, California had the highest value. Let's go back and view it. Here it is. California has the highest value there, and Montana has the lowest at 482. Now, the range is highest minus lowest. So this is the highest from there to there, and this is the lowest. So it's a total of 739. Now what we do is we take this 739 and divide it by the 7 classes which we saw in the previous step. Okay, so 739 over 7 gives us 106. What this is saying is that if we were to use 7 classes, okay, then each width of every class should be $106 wide. $106 is a good number, but unfortunately is not easy on the eye. So we need a number, a width, class width, which is easier on the eye, easy to mentally calculate. So good numbers such as 10, 50, 100, 150 and so on would be ideal. So how do we make this 106 smaller? Well, in primary school we were taught that if you divide by a larger value, you get a smaller number as the answer. So here it is. How about if we increase the number of classes to 8? So the range, 739 over 8, will generate a class of 92. Sorry, a width, class width of 92. What does that mean? It means that now we can have 8 classes of 92 each. So now we can safely round up this 92 to $100. So we can have 8 classes and each class will be $100 used. One other important thing to note is that if you take this 8 and you multiply it by 100, you will get 800. The 800 is more than the 739. And this is very, very important, because the total width of classes, so 8 times 100, must be greater than the range. This ensures that we haven't missed any data. The next step is we have to select our lower class limit. Okay. Ideally it should be a number which is easy on the eye, ideally. So if we say start with 450 and we keep repeatedly adding one of these, because it has to be 100 wide for each class limit, we get 450 up to, but not including, 550 for the first class. Then we move to the second class, 550 up to, but not including, 650, and so on. So the first class is this, all the way through to the 8th class. One thing you have to note is that the lowest limit of the first class is smaller than, I emphasize, is smaller than the smallest value in our data set. If you recall, it's the value of 482, which belongs to Montana. And the upper limit of the final class, 1250, is greater than the value of California, which was the highest in our data set. Next step is to count how many countries or how many states belong in each category. So if I go back to the original data, okay, I see that if I start from the bottom right, 1, 2, 3, 4, 4, okay, from Montana to Wyoming, from 4 belong in the class of 450 up to, but not including, 550, and so on. And if I keep doing the same for all classes, I see that in the first class we get 4, in the second 3, in the third 7, all the way through to the last one with 1. Okay, each class has a width of 100, and the class marks are the midpoint. So the midpoint for the first class, it's 550, the midpoint for the second class, it's 600, and so on, all the way through to the last one. The midpoint for the last class is 1200. As a safety check, if you add all these here, they must, I emphasize, these numbers here, they must add up, the frequencies must add up to 50. If they don't add up to 50, you've made a mistake. You may have forgotten one or added one too many. So you have to go back and check. So ensure that. The next step is to create a frequency distribution. How do we create a frequency distribution? Effectively, if you take this, okay, which is the frequency distribution that's already created. What I meant here is how do we create a histogram out of the frequency distribution. If you take the frequency distribution and you rotate it by 90 degrees, okay, say to the right, what we do get is all the classes on the bottom, no longer on the right hand side but along the horizontal, and these are the frequencies. So we know in the first class, which has a midpoint of 500, i.e. from 450 to 550, there are 4 states. In the second class, between 550 and 650, there are 3 states, and all the way through to the last class. Note one thing, that in a histogram there is no gaps between bars, and immediately we can tell that the vast majority happens in this area, somewhere between 700 and 900. One more thing we have to worry about is the so-called relative frequency. Recall, relative frequency means that we add up all these values, which should add up to 50, and then we take each of these and divide through by the total 50. Here it is. So 4 over 50 is 0.08 or 8%, for example, if it is presented as percentage, and so forth. So the next one would be 6%, and so forth. As long as you're consistent, you don't have to be doing percentages, but you must, I emphasize, you must be consistent in your data. And the last step that was asked of us in this question was to create a cumulative frequency and a cumulative relative frequency. Now, a cumulative frequency, we just continue with our frequency and we accumulate as we go along. So we know that between 450 and to under 550, so in this class there are 4. Here it is. However, if we start at 450 to under 650, we must add up the 3 and the 4 we already have, so we get 7. From 450 to under 750, we have 4 plus 3 plus 9, which is 16, which is the same as 7 plus 9, and so on, all the way to the last one. And we know that in total between 450 to under 1250 there are exactly 50 states. This is with frequencies. We can do the same thing with cumulative frequencies from previously, so with these values here. So we add up the 0.08 plus 0.06 and so on as we move along. And what we get is 0.08, 0.14, 0.32, 0.50 and so forth, or as percentages. As a safety check again, the last value must, I emphasize, must equal to 1 or 100%. This slide wraps up the first part of this chapter. I hope you enjoy it and look forward to having questions from you in class and doing plenty of exercises. In the next part of this chapter, we'll start looking at some numerical descriptive data. How do we actually calculate things in statistics?